After implementing a binary neural network classifier in the last section, our new goal is to implement a multi-class neural network classifier. The obvious way to support multi-class classification is just to tackle in a one verse rest or one verse one system, just like we did with the perceptron. The biggest drawback to this is that it means we'd have to train at least as many models as we have classes, and sometimes we might have hundreds or even thousands of classes. And training hundreds or thousands of neural networks would take a very, very long time. So we'll take a different approach. Suppose that instead of having a single output node in our neural network, we had multiple output nodes, one for each class of our target variable, where the value produced by output node k is the probability of class k. Clearly, this would be a usable multi-class model. The questions we have to answer are, how do we ensure the output probabilities sum to 1, and how do we adjust our loss function and our learning algorithm to support this? Let's think about that second question. For a given input sample, how do we calculate how good or bad a prediction is, keeping in mind we still need to have a differentiable scoring function? Lucky for us, log loss is actually a special case of a more general loss function called cross entropy, which does exactly what we need. For a single observation, cross entropy equals the negative sum over k of pk times log of qk, where pk is the true probability of class k, and qk is the predicted probability of class k. Notice how if k spans two classes, this is exactly log loss. For us, exactly one of these pk's is 1, and the rest are 0. So we can simplify the whole expression to negative log of y hat k star, where k star is the index of the correct class. And just like log loss, we can calculate the average cross entropy over all samples. What about the gradient of cross entropy? Well, we want to know how cross entropy changes with respect to small changes in each of the predicted class probabilities. Keep in mind, for a single sample, y looks something like this, and y hat looks something like this. In this case, the gradient of cross entropy with respect to y hat is going to equal this row matrix of partial derivatives, which resolves to this. Notice every term is 0, except for the term corresponding to the positive class, which is negative 1 over y hat. So our updated network diagram looks something like this. The next question is, how do we make sure our predicted probabilities for a single observation sum to 1? Just as cross entropy is a multidimensional extension of log loss, it turns out that the softmax function is a multidimensional extension of the logistic function. It works like this. Given a vector of unbounded real values z like this, softmax of z produces a new vector with the same length, where the kth element of the new vector is defined as e to the zk divided by the sum over k of e to the zk. To put it another way, softmax is like a two-step algorithm. The first thing you do is raise e to the power of each element in the original vector. Then, you divide each of those guys by their collective sum. Intuitively, you can think of softmax as a function that squashes values into probabilities, where higher values translate to higher probabilities. For instance, if z was this vector, e to the z would be this vector, and softmax of z would be this vector. Looking back at our neural network, instead of having a logistic activation function at each of the output nodes, we'll have a single softmax function. Note that with softmax, each y hat depends on every z in the last z layer. Next question. What's the gradient of the softmax function? Or rather, since it's a function that maps a vector to a vector, what's the Jacobian of the softmax function? The Jacobian is just the matrix of partial derivatives that looks like this. Well, Sj is defined as e to the zj divided by the sum over e to the z. So if we think about partial Sj partial zk, we can break it into two cases, where k equals j and where k is not equal to j. And with some help from the chain rule and a little algebra, we get partial Sj partial zk equals Sj times 1 minus Sj when j equals k, and negative Sj times Sk otherwise. Now our job is to calculate the gradient of cross entropy with respect to W1 and W2. We'll approach this just like before, starting at the end of our network and working our way backwards with the chain rule. The first step is to calculate the gradient of cross entropy I with respect to y hat I, which we already did. So we'll just recall that CEI equals this. So the gradient of CEI with respect to y hat I is this. And keep in mind that the only non-zero term in this row matrix is the one that corresponds to the correct class. Next, we want the gradient of cross entropy I with respect to Z2I, which is going to be a row matrix like this. We can use the multivariable chain rule to expand these terms into the following, because each z feeds into each y hat, and each y hat feeds into the final cross entropy. But most of these terms are going to be zero, because only one yk is not zero. So if we denote the true class index for the ith sample as k star, we can rewrite this matrix like this. Then we can pull out partial CEI partial y hat I k star, which we know is equal to -1 divided by y hat I k star. So then we have to deal with these terms, which basically ask the question, how does our prediction for the correct class change with respect to small changes in the Z2 terms? Well, the y hat layer comes from applying the softmax function to the Z2 layer. So let's recall the softmax derivatives we found earlier. So with this, we can define partial CEI partial Z2ik equal to -1 divided by y hat I k star times this piecewise function, which ultimately simplifies to this. And then this tells us that partial CEI partial Z2ik equals y hat ik, except we subtract 1 from the term corresponding to the correct label. Well, a sneaky way to rewrite this guy is just y hat I minus yi. Next, let's determine the gradient of cross entropy I with respect to W2. If we think about this first term, partial CEI partial W211, we can use the chain rule to rewrite that guy as partial CEI partial Z2I1 times partial Z2I1 partial W211. Well, we just calculated partial CEI partial Z2I1, so we only need to determine partial Z2I1 partial W211. And that's pretty simple. It's just x2I1. So if we generalize this to the whole matrix, we get this matrix product, which we recognize as x2I transpose times the gradient of CEI with respect to Z2. Next, let's figure out the gradient of cross entropy I with respect to x2I. Well, this follows nearly the same logic as the last gradient we just calculated. So pretty quickly we can figure out that this equals the gradient of CEI with respect to Z2 times W2 transpose. And then from this point onward, we're really just repeating the same steps we did in the last section, so we can literally reuse our old work. So to recap, here are all the gradients we'll need to calculate. And then our batch update process looks like this, very similar to what we had before. Now let's think about the code. We're going to need some new helper functions, the first of which is softmax. Recall that if you have a vector of values z, and you apply softmax of z, you get back a new vector where the jth value of the output equals e to the zj divided by the sum of e to the z. So we can code up a pretty simple row-wise softmax function like this. Next, we make a one-hot function that inputs a 1D array of labels and returns a tuple of two things, a 2D array of one-hot encoded values and a 1D array of unique classes, where the kth value in the class array corresponds to the kth column in the one-hot array. Next, we make a cross-entropy function that inputs arrays y hat and y. Y hat should be a 2D array of predicted probabilities, and y can either be a 1D array of true indices or a 2D array of one-hot encoded true indices. This function returns row-wise cross-entropy values, so if the input arrays have length n, the output array is also going to have length n. Lastly, we'll reuse the logistic function we created in the last section. Now pause the video and see if you can implement a neural network class that supports multi-class classification with softmax activation on the output layer and cross-entropy loss. Here's the code I came up with. Frankly, there's nothing too earth-shattering in my code. It's pretty much the same as it was in the last section, except I incorporated the softmax function and cross-entropy loss. Also note that the way I determine which class label the model predicts for a given sample is by determining the class index with the highest predicted probability using NumPy's argmax function. Let's see how our multi-class neural network performs on the simple images data. Here, we use virtually the same setup as the last section, except in this case, we use the raw image labels for the target y instead of binary indicators for whether each image is a checkerboard. After 10,000 gradient descent steps, we evaluate our model on the test data and see that it's about 98% accurate. Not bad.